start of the 21st century saw many discoveries being made in the field of physics that weren't exactly the most intuitive or logical, but drastically revolutionized the way in which we perceived our world. One of these discoveries came in the form of blackbody radiation. And what this is, essentially, it's the electromagnetic waves or radiation that is emitted by hot objects. And the actual radiation that is emitted varies with temperature. So, if you have an object that is at a very high temperature, it's going to emit electromagnetic waves with a high frequency or low wavelength. In other words, if you have an object that is high temperature, it's going to emit waves with high energy. And you already know this because if I gave you a rod and it was glowing orange, so if you have a glowing orange rod, and we compare that to a glowing red rod, we'll put it here, a glowing red rod, and I asked you which one was hotter, you would likely say it's the orange rod, just from intuition or past experiences. And this agrees with what we just said, since the frequency of orange light is higher than the frequency of red light. Likewise, and this example might be even more clear, if you had a blue flame, you have a blue flame and we had an orange flame or a red flame, and I asked you which one would be hotter, you would most certainly say it would be the blue one. And once again, this agrees with what we just said, since the frequency of blue light is higher than the frequency of orange or red light. And so essentially, the reason why this occurs is because hot objects have oscillating charges within their atoms. So if we imagine we have a rod and we zoom in at this rod, it's consisting of lots of atoms, and if we zoom in into one of these atoms, it's surrounded by electrons and a variety of other subatomic particles. And at high frequencies, these particles essentially vibrate, or they oscillate up and down, and this oscillation is what gets transferred into an electromagnetic waves. And so the frequency of the oscillation is directly proportional to the temperature of the rod. If it's high temperature, it's going to oscillate a lot, and if it's a lower temperature, it's going to oscillate less, since temperature is directly tied to energy. And so at high temperatures, you have a high frequency of oscillation, which is transmitted as a high frequency electromagnetic wave. So we can graph what we observed experimentally from the electromagnetic radiation emitted by black bodies. So on our graph, we'll have wavelength as the x-axis measured in nanometers. We'll start at 100 nanometers and go to 2,500 nanometers. So over here, you would have your X-rays and UV rays. And on the right, you would have your radio waves and IR. So we're going from high energy or high frequency to low frequency. And on our y-axis, we would have the energy intensity or relative intensity of the emitted electromagnetic waves, and this would be measured in Kelvin. And if we plotted what we observed, we would end up with a mound that looks something like this, where your visible light region is somewhere in the middle. Now, the problem was when they tried to model this trend using the classical equations, so the equations they had previously, using these classical equations that governed electromagnetic waves, they predicted too much radiation in the UV region. So when we tried to model this, what we'd get theoretically is that the energy would increase, and then when it nears the UV region, it would simply skyrocket up to infinity. And this wasn't possible experimentally. It didn't make any sense because energy had to be conserved, so you can't get infinite energy from nowhere. And it turns out the problem is that we thought energy was a continuous quantity. So your energy could be anything, any number that you thought of could be a possible energy. It was a continuous spectrum. But it turns out that energy is actually discrete, and it comes in packets. And we'll talk about that more in a few seconds. So before scientists discovered that energy was actually a discrete quantity rather than being continuous, they did have an equation that would describe the maximum wavelength that was emitted by a black body at a given temperature. This is called Wein's law, and it states that the maximum wavelength is equal to 2.90 times 10 to the negative 3, which is simply a constant, meters Kelvin divided by, so this quantity is in meters Kelvin, divided by the temperature of the object in Kelvin. So if you're given a temperature of an object in Celsius, you're going to have to convert it to Kelvin such that your units work out for this equation. And we note that this is the maximum wavelength, since if you have an object, it might be emitting electromagnetic waves throughout the spectrum, and this equation will give you the maximum wavelength, or the smallest frequency of the EM waves that can be emitted. So we have a question here at the bottom. We have a hot rod that is glowing a light color of blue. So we have a rod that is so hot that it's glowing a light color of blue. And the blue light, will assume that the maximum wavelength of this blue light is 400 nanometers. We want to know what the temperature of the rod is in Kelvin. So we can use Wein's law. We have lambda max is equal to 2.90 times 10 to the negative 3 meters Kelvin. Our temperature is what we're trying to solve for, and our lambda is given as 400 nanometers. So we can isolate for our temperature by dividing by lambda and then multiplying by temperature. We get that the temperature is equal to 2.90 times 10 to the negative 3 meters Kelvin divided by our maximum wavelength, we're going to assume, is 400 nanometers. We'll convert that to meters so we can work with SI units. So 400 times 10 to the negative 9 meters. And if you plug that into your calculator, you'll get a final answer of 7,250 Kelvin. So assuming that the maximum wavelength emitted by the rod is 400 nanometers, then the rod is 7,250 Kelvin in temperature. So returning to the concept of energy, in order to create a working model for blackbody radiation, Max Planck had to consider energy as being discrete. And what this means is that rather than being continuous in nature, it was transmitted in small packets. And these packets are what he called quanta. So it's very similar to the idea of charge. So charge is also discrete because you have your minimum charge, which is the charge of an electron, or 1.602 times 10 to the negative 19 coulombs, and all other charges are a integer multiple of the charge of an electron. So it's the same idea here. We have energy, and we have a minimal energy, which is the energy of one quanta, and all other energies have to be an integer multiple of this minimum energy. So this is essentially just a minimum amount of energy. So if we had a continuous beam of light, where we used to imagine it as a continuous wave, instead Planck is saying that it's composed of many smaller wave packets called quanta. And the energy of a quanta is directly proportional to the frequency of the electromagnetic wave it came from. And this is shown through the equation, or Planck's equation, where E is equal to hf, where h is equal to Planck's constant, or 6.63 times 10 to the negative 34 joule seconds, and f is the frequency of the wave. Of course, f is in hertz, or reciprocal seconds, or 1 over s, so h times f is joule seconds times 1 over s, and your final answer for energy is going to be in joules. And all Planck is saying is that the energy of a wave has to be an integer multiple of the minimum energy, or the energy of a quanta, so nhf, where n is an integer. So it's either 0, 1, 2, up to some whole number. So just like electrons, quanta are very small quantities. Quanta are very small. And so the numbers we get from dealing with quanta are also very small. And you can see that from the equation. Since the energy of one quanta is equal to hf, and h is equal to 6.63 times 10 to the negative 34. So our order of magnitude here is 10 to the negative 34. It's very small. And for this reason, scientists created a new unit when dealing with these small quantities called the electron-volt. And an electron-volt, 1 electron-volt, is equal to 1.60 times 10 to the negative 19 joules. So essentially, it was created to be able to better understand and make sense of these very small quantities. So whenever we're dealing with these quanta, we're usually going to be using the electron-volt, or EV for short. So now as a question to practice with the equation, we want to find the energy in one quanta of blue light. So usually we'd see blue light as a continuous wave, but as Max Planck said, it's composed of smaller wave packets, and each one of these wave packets has its own energy, making the energy of the wave discrete. So the energy of one of these wave packets, which we'll call E, is equal to Planck's constant times the frequency of the wave itself. The frequency of the wave we're not given, but we're given its wavelength. So the wavelength is equal to 400 nanometers. And we know for any wave, its speed is equal to its frequency times its wavelength. And so we can find the frequency by dividing the speed of the wave. Since it's an electromagnetic wave, it's moving at the speed of light, or c, which is 3 times 10 to the 8 meters per second, divided by the wavelength. And so the energy of one quanta is equal to Planck's constant times the speed of light divided by the wavelength of the wave. If we substitute in, we get 6.63 times 10 to the negative 34 joule seconds times the speed of light, so 3 times 10 to the 8 meters per second, divided by the wavelength. We're going to be wanting to work in meters, or SI units, so we'll convert 400 nanometers to 400 times 10 to the negative 9 meters. And if you plug that into your calculator, you'll get a final answer of 4.9725 times 10 to the negative 19 joules. So this quantity is very small, so we're going to switch over to electron volts. So if we take that energy, 4.9, or the energy is equal to 4.9725 times 10 to the negative 19 joules, we'll multiply with our conversion factor, 1 electron volt divided by 1.60 times 10 to the negative 19 joules. So joules and joules will cancel out, and we get that our energy is equal to 3.11 electron volts, which is much more understandable and better to communicate with. So therefore, a quanta of blue light is approximately carrying 3.11 electron volts of energy. And you can notice here from the beginning that we have seconds canceling with seconds, meters canceling with meters, so all we're left with for our energy, once again, is joules.